Hi, today we're going to look at question 6 from step 1 from 2018. I'm making a whole series of these videos so you can find a playlist with all the ones that I've done so far. I'll link that below. This question starts by asking us to use this identity here, 2 sine p sine q is cos q minus cos q plus p, to show that this statement here is true. And you can see, if I was to multiply out these brackets, we would get statements a bit like this one, at least a bit like the left hand side here, 2 sine theta, 2 sine theta, sine 3 theta. So I'm going to start just by writing out some of those, and it'll become quickly apparent how this works. So if I had 2 sine theta times sine theta, so I'm taking both p and q to be theta in this identity, I'm going to have cosine of theta minus theta, which is 0, minus cosine of theta plus theta, which is 2 theta. If I look at the next term in the bracket here, 2 sine theta times sine of 3 theta, then I would get cos of 3 theta minus theta, which is 2 theta, minus cos of 3 theta plus theta, which is 4 theta. And you can see, if I keep doing this, that we're going to get a lot of cancellation when we add all of these together, right? Because I've got minus cos 2 theta here, plus cos 2 theta here, minus cos 4 theta, plus cos 4 theta. Okay, so I keep doing this until I get to the last term, which is 2 sine theta sine 2n minus 1 theta, and that one gives me cos of 2n minus 2 theta minus cos of 2n theta. So if I now add all of these together, okay, plus sine of 2n minus 1 theta, I'm not going to write this out any more formally, but I'm just going to say here that I'm going to get sort of these cancelling out when I do this, and so I'm going to get just cosine of 0, and then everything cancels out right until the end here, which is the cos 2n theta is the only one that I'm left with, so minus cos 2n theta. Cosine of 0 is just 1, of course, so I get 1 minus cosine 2n theta, which is exactly what we're required to show. Okay, so a little bit tricky with this sort of telescoping sum idea here, but as soon as you start, I really recommend, if you're not sure where to start with one of these questions, just find some part of the question that you can work with, write a few statements out, don't worry about proving the thing as a whole. Sometimes as you start to write down the reasonably obvious things, the more complicated things will start to emerge. So in part 1, we want to let an be the approximation to the area under the curve y equals sine x from x equals 0 to x equals pi, using n rectangular strips, each of width pi over n, such that the midpoint of the top of each strip lies on the curve. Okay, so let's just draw the graph of sine x between 0 and pi. Looks something like this, and the idea here is then that I'm going to have these rectangles where the midpoint of the rectangle is exactly on the curve, and I'm going to have n of these in total. So I'm just doing this approximately. Okay, my last rectangle's hasn't quite worked, but you get the idea. Right, so we just need to know what the x coordinates of these points are then. Well, if I've got n strips that are pi over n in width, so this point here is going to be pi over n, so actually this midpoint here is going to be that divided by 2, so it's going to be pi over 2n, right? So the next point is going to be that plus pi over n, so it's going to be 3 pi over 2n, then I'm going to get 5 pi over 2n, and I'm going to keep going up here until I get to the last one here, and that's obviously going to be pi minus pi over 2n, right, which is 2n minus 1 pi over 2n. Okay, and you can think about that carefully if that's confusing. But of course, each of these rectangles has width pi over n, and the heights of the rectangles then are just going to be, well, this is the graph of y equals sine of x, of course, so you know the height of this first one is just going to be sine of pi over 2n, the next one will be sine of 3 pi over 2n, etc. Right, so my approximated area is just going to be, you know, pi over n times sine of pi over 2n plus pi over n times sine of 3 pi over 2n, etc. I'm going to keep going until I get to pi over n times sine of 2 pi minus 1, 2n minus 1 pi, sorry, over 2n. Okay, and I could write that a little bit more compactly here using sigma notation, right? So I could say that's pi over n times the sum from k equals 1 to n of sine of pi 2k minus 1 pi divided by 2n. If you want to write that in more compact notation, and again you can just check that each of the terms corresponds to exactly what I've written here. So the question asks us to consider actually an times sine of pi divided by 2n. So actually we can write this then as pi over n times the sum from k equals 1 to n of sine of pi over n times sine of 2k minus 1 pi divided by 2n. And notice there's no problem at all here bringing this sine pi over 2n, or we should 2n here of course, bringing this inside the sum because it doesn't depend on k, right, only on n, which is fine. Now if you look at this carefully, so this sum, actually it might be clearer if you write it out in longhand here, but it's exactly the thing from the introduction, okay, where we take theta equals pi divided by 2n in that first statement that we've proved, right? So again, you can write that out really carefully again if you need to, if that's not clear. But what that means is that I can replace this whole sum with, well, we actually get a half times 1 minus cosine of 2n times pi over 2n, right? So what I'm doing here is going back to that previous statement here and saying, okay, if I take theta to be pi divided by 2n, then this whole thing is the sum. Actually, there was a 2 here as well, so I'm dividing by 2 on this side, and if I put theta equals pi over 2n here, this becomes cos of 2n times pi over 2n, which is exactly what I've written here. So of course these 2n's cancel, and I just get pi over n, or pi over 2n, that's right, 1 minus cosine of pi. Cosine of pi is minus 1, so I've got 1 plus 1 is 2, and then the 2's cancel, so I just get pi divided by n, which is exactly what the question asked us to show. Okay, so getting a little bit trickier. In part 2, we asked to do the approximation again, but rather than using this midpoint rectangle rule, we are going to use the ordinary trapezium rule with n strips, each of width pi by n. Okay, so I think you're probably more familiar with the trapezium rule from A level perhaps. It's the one that you're examined a bit more. So this approximation Bn, I'm going to jump straight in and say that the trapezium rule here says that it's the strip width, which is pi divided by n, and then I multiply that by the two endpoints. Okay, so that's sine of 0 plus sine of pi, and then I do 2 times all of the heights of the middle parts of the trapezium rule. Okay, go back and think carefully about the trapezium rule if this isn't clear, but I'm just going to write then the sum from k equals 1 to n minus 1 here of sine of k pi by n. Okay, so perhaps let me just make that slightly more clear. So here now I'm looking at trapezium rule strips, so this time the endpoints of my trapezium rules are the ends of the strip widths, right? So the first one is 0, the next one is at pi by n, and the next one is going to be at 2 pi by n, right? So the trapezium rule says, okay, do the two end values are only in one of the strips on one trapezium each, but all of the middle ones, are part of 2 trapezia. So we add all of those together, and we get this. Now, of course, sine of 0 and sine of pi are both 0, so actually these are both 0. So here we're just left with this middle term. Okay. Oh, and the trapezium rule also has a half in it, doesn't it, as well? So I should put that at the front here. And then the half and the 2 cancel out. So I'm left here just with pi divided by n times the sum from k equals 1 to n minus 1 of sine of 2, well, okay, I'm going to write this k pi over n as 2k pi over 2n, and you'll see why in a second. So if I do bn times sine of pi divided by 2n, I just get pi divided by n, sum from k equals 1 to n, of sine of 2k pi over 2n times sine of pi divided by 2n, right? And now if we go back to the to one of the original statement here, 2 sine p sine q is cos q minus p minus cos q plus p. I'm going to just apply that to this statement here, right? Because I've got sine of something times sine of something else, so I'm going to take this to be p and this to be q in that statement. So I get pi over n times the sum from k equals 1 to n of cosine of p minus q, so that would be here 2k minus 1 pi over 2n, and then I'm going to get minus cosine of p plus q, so I'm going to get 2k plus 1 pi over 2n. Okay, and now if you start writing this out, again you'll see we've got another kind of telescoping sum here, because this first one, so I'll start with k equals 1 here, and we will get cosine, oh, and I think I need a half here as well, sorry, from that identity. I'm doing very well with these halves today. That half comes just from the 2 in front of this identity here. So I get pi over 2n times cosine of pi over 2n times cosine of pi over 2n, and then the next, and then I'll have minus cosine of, now 2k plus 1 for k equals 1 will be 3, so that'll be 3 pi over 2n. But now when I go to k equals 2, you see I add on in the first term here cosine of 3 pi over 2n, and then I subtract cosine of 5 pi over 2n. So you see we're going to get this this telescoping sum again. So I'm going to keep going until finally I get the last term here, which is going to be cos of what I get when I put in oh, I'm sorry, I'm making lots of little typos today. This sum should be going to m minus 1. That doesn't make any difference, because with n here I would just get a 0 term from the pi, but let me stick to n minus 1 to be consistent. So with n minus 1 here I get 2n minus 1 plus 1, which is just 2n minus 1 like this, divided by 2n times pi. Okay, so I've got pi over 2n, everything cancels apart from cos of pi over 2n minus cos of 2n minus 1 over 2n pi. And now just think about, okay, so it's important to be able to spot some symmetries here. So if I have the graph of, cosine, what we're looking at here is two values of cosine right here. I've got cosine of pi over 2n, and 2n minus 1 over 2n pi is just the same thing as pi minus pi over 2n, right? So whatever the value of cos of pi over 2n that's just minus the value of cos of pi minus pi over 2n. So this is just so actually I get minus minus, and I just get just get 2 of these. Okay, and then of course the 2's cancel, and I get pi over n cosine of pi over 2n, and again that's exactly what we were required to show there. So this is a little bit more involved than some of the other questions perhaps. I mean, all the step questions are a little tricky. But we've still got a third part to do, and it says show that these two statements are true. So I've got a half an plus bn equals b2n, and also this second one here, an b2n is a2n squared, and I've just put here in the top right here a reminder of the expressions that we've derived for an and for bn here. So let's do the first one then, right? So okay, so these identities both have sine pi over 2n, so I think I felt it was quite natural here to write for the first one actually, rather than a half an plus bn, to write a half an plus bn multiplied by sine of pi divided by 2n, and then I'm just going to get, you see, an times sine pi over 2n, so I'm going to have a half here of pi over n plus this bn, which is pi over n times cos of pi over 2n. So actually if I pull this pi over n out, I've got pi over 2n 1 plus cos of pi over 2n. And our target here is b2n. Now if you think about it, so if I replace n with 2n in this identity, I get b2n sine pi over 4n is pi over 2n pi over pi over 2n cos pi over 4n. Okay, so I've got an identity here I've got something with cos pi over 2n, and I know I need to kind of have something with cos pi over 4n, which is a half of pi over 2n. So that makes us think of the double angle formulae, right? So one of them is that cos 2 theta is 2 cos squared theta minus 1, so I get that 1 plus cos 2 theta is 2 cos squared theta, right? So if I took theta here to be pi divided by 4n, so 2 theta is pi divided by 2n, right? Then this 1 plus cos pi over 2n is just 1 plus cos 2 theta, so that's just the same as 2 cos squared of pi over 4n. Okay. Right. So we're getting quite close. I've still got this sine pi over 2n on this side, so if we also use the identity sine 2 theta is 2 sine theta cos theta, again with theta equals pi divided by 4n, then this sine pi over 2n becomes 2 times sine of pi over 4n times cos of pi over 4n. So, and okay, my 2's have cancelled on this side, so I've got pi over n cos squared pi over 4n, right? And now okay, I can cancel one of these cos pi over 4n's, this one here, with one of the ones from the square. Okay, and then if I move the 2 sine pi over 4n to the right hand side by dividing by it, I get 1 over 2 an plus bn is pi over 4n times cos pi over 4n over sine pi over 4n. And if you look at this statement here about b of 2n, well, if you just pull that sine pi over 4n down here, that's exactly what we've got here then. Oh, sorry, I've written 4n here because everything's 4n, but again, this is actually 2n. Just a typo in my in my division there. Sorry about that. I'm missing a lot of these 2's here today. So I've divided by that 2. Okay, but it says the 4n is inside the cos and the sine, but 2n here. So I get exactly what I want. That is equal to b of 2n. Again, it's going to say here as required to show that I've got to the end there. Okay, last part then. an b2n is a squared 2n, and that's going to go in a similar sort of way. Let's have a clean page for that. So we have that an times b of 2n then. If I just write down what we've got here, so an, at this time let me just write it directly with the sine pi over 2n divided, so I'm going to have pi over n 1 over sine pi over 2n, that would just be an from this formula. And then for the b2n, I'm going to write that as pi over 2n times cos of pi over 4n over sine of pi over 4n, which again is just this with 2n in it, exactly as I'd written down on the previous slide. Okay, so now again, it's quite useful to sort of think about, where we want to end up here, right? We want to end up with a 2n squared, and in this statement here, if I write it with 2n, I get a 2n sine pi over 4n is pi over 2n. Okay, so actually a 2n squared is going to be pi over 2n squared times 1 over sine squared pi over 4n. So actually, that's really what we're hoping to get at the end of this argument. Okay, and this is actually, if you're stuck as to how to where to go with one of these, actually writing down a target like this is not a bad idea, because one thing I can see here is that I really only want to have things with pi over 4n in them. In this identity here, I've got sine pi over 2n, so again I want to use sine 2 theta is 2 sine theta cos theta, with theta equals pi over 4n, so 2 theta is pi over 2n, and I can just replace this sine pi over 2n with 1 over 2 sine pi over 4n cos pi over 4n, and then I've got still pi over 2n cos pi over 4n divided by sine pi over 4n, and we can see we get a cancellation of those terms. And in fact, if I start to gather all of these terms together, look, I've got pi over n, and I've got a 2 and a 2, so that gives me my pi over 2n squared. Oh, and I've got sine pi over 4n times sine pi over 4n. So actually I've got my sine pi over 4n squared here, so I don't really need any other line here. Let's just say they're equal. Okay, so that's the end of this question. I hope that was useful. Let me know in the comments if you have any better ways of doing it, or if there's anything that's not clear. Sorry I kept missing all those 2's. I hope it didn't distract from the argument too much. So I'm putting these all into a playlist. I'm hoping to at least to finish this step 1 paper at some point soon, and we'll move on perhaps to some of the step 2 and 3 questions as well if you're looking at those. So I will see you in the next video.